Hello there. My name is Nick Huntington Klein. I'm a professor of economics at California State University, Fullerton. And there's a problem, a mathematics problem that I think is particularly interesting. And not just because of the math that it is, but also because of how interesting it is to see people try to understand what their actual correct result is and to believe their correct result when it's presented to them. And that's the Monty Hall Problem. So what I'm going to do in this video is talk about what the Monty Hall Problem is, and I'm going to give you 9 different explanations of why the answer to the Monty Hall Problem is a little surprising. And I'm going to try to do it in 10 minutes. So let's see if I can do that. So first, what is the Monty Hall Problem? So this is based on an old game show featuring the presenter Monty Hall. And basically in the Monty Hall Problem, you'd be presented with 3 doors. And behind one of the doors is the grand prize, a car. And behind the other 2 doors are goats, which you don't want. So your goal is to try to pick the door that has the car behind it. Now, you're going to pick a door. I'm just going to say I'm going to pick door number 1 right here. But the game's not over. Okay? So what Monty's going to do is Monty's going to look at the other 2 doors and he's going to open one of them for you and show you what's behind that door. Now, this is important. Monty knows where the car is and he's not going to show you the car. He's going to open one of the other 2 doors behind the other 2 doors that has a goat behind it. Okay? So he's going to open one of these doors. He's going to open door number 2 and show you that there's a goat. So now there's only 2 doors left, the one that you picked and the other one. Now the question is, are you more likely to win if you stick with the door that you chose the first time, or if you switch to the other door, or does it not make a difference? Now, at first blush, a lot of people are going to say that it doesn't make a difference. There's 2 doors. Each of them was equally likely to have the goat or the car behind it. So 50-50, right? Actually, no. You have a 2/3 chance of winning if you switch, and only a 1/3 chance of winning if you stay. So that's what the Monty Hall Problem is. Now I'm going to spend the rest of the video talking about why what I just said is correct. So the first explanation is just to point out that of those 3 doors, you had a 1/3 chance of being correct with the first time that you picked. Whatever door you picked, each door is equally likely to have the car behind it. So we're going to pick this door. We're going to pick door number 1. Okay? There is a 1/3 chance that you were correct, right? 3 doors, each of them equally likely, 1/3 chance. That's going to stay true no matter what else happens, that the original door had a 1/3 chance of being correct. So open this door, show that it's these 2 left. This door still had a 1/3 chance of being correct, which means that door has all the rest, the 2/3. So you switch, you get 2/3. You stay, you only have 1/3. For explanation number 2, I'm going to draw a tree that might make it a little bit easier. So what I'm going to draw on this tree, one of these lines, you have picked the car, right? Because there's a 1/3 chance of picking the car. The other 2 are goats, okay? From each of those, we're going to draw 2 more branches because you could either switch or stay. If you picked the car and you switch, that means that you are going to lose, right? Because you were already on the car, you switch to a goat, you lose. Now, if you're on either of the goat paths and you switch, that means that you win. You picked the goat, right? And he's going to open a goat, which means that the one he didn't open has to be the car. So if you started with the goat and you switch, you get the car. If we switch, then that means that we lose if we started with the car, and we win if we started with the goat. However, 2/3 chance we started with the goat, 2/3 chance that switching is going to win. What if we stay? If we stay, that means that if we pick the car, we win. But if we pick the goat, then we lose. Staying means that we're only having a 1/3 chance of winning. So what I'm going to do for explanation number 3 is I'm going to represent probability as an area. I'm going to draw 2 rectangles. One of these rectangles represents the probability of what could happen if you switch. Now, in both rectangles, there is a 1/3 chance that you started out picking the car, right? So I'm going to draw a 1/3 over here and a 1/3 over here, and that is the region that you are in if you pick the car, right? Equal chance of being anywhere in these rectangles. 1/3 chance that you started with the car, which means that that 1/3 of each of these rectangles is the car. I'm going to color in this area where you started out picking the goat as win, and this area where you started out picking the car as a loss. And then over here on the right, win if you picked the car first. So I'm going to put a win in the car area. There's a 2/3 chance of winning on the switching rectangle, and there's a 1/3 chance of winning on the staying rectangle. So that's explanation number 3. So all these explanations, how is it possible that there's only 2 options left and yet it's not 50-50? Whatever argument I give you, you might think, well, whatever you say, there's 2 options left. It was equally likely to be either of them. It's got to be 50-50. And the reason it's not the case is because Monty gave you some information, right? Monty knew where the car was, and by making a choice based on knowing where the car was, he gave you information that you didn't have before that makes it not 50-50 anymore. Because if you just looked at those 2 doors from the start, well, yeah, 50-50. But it's not looking at those two doors from the start. It's looking at those two doors after Monty has sent you an informative signal, which should change your beliefs about where the car is. So for explanation number 5, let's sort of illustrate that a little bit. What would happen if Monty did not know where the car was, and so just sort of happened to open a door at random? No, let's just imagine for a second, if Monty opens the car, the game just sort of ends. Now there's 3 possibilities, each of which is equally likely. So initially pick the car, and then Monty opens a door revealing a goat, okay? There is a 1/3 chance that that happens, and if you switch, then you lose, and if you stay, then you win, okay? There's also a 1/3 chance that you pick a goat door, and then Monty will open a goat door, right? Because there's 2 goat doors, so there's a 2/3 chance that you picked a goat door, and half the time, he's gonna show you a goat door rather than the car. So 2/3 times a half is 1/3. So it's exactly 1/3 chance that you pick a goat door, and Monty will open a goat door for you. Now, in that case, if you switch, then you win, and if you stay, then you lose. There's also a 1/3 chance that you start with a goat door, and Monty opens a car door, and the game ends immediately. Okay, so 1/3 chance the game ends immediately, can forget about that. 1/3 chance that you start with a goat door and switching would win. 1/3 chance that you start with a car door and switching would lose. So there's a 1/3 chance that switching wins you, 1/3 chance that switching loses you, and a 1/3 chance the game just ends immediately. But we can forget about that, so now it's 50-50, right? If Monty does not know where the car is, that makes it 50-50. But the fact that Monty does know where the car is in that original game means that he is sending you a signal, which makes it possible for it to not be 50-50. Let's illustrate this fact that Monty's giving you information in another way. Let's call this game Aces, and it would not be very fun to play. I'm going to draw 5 cards. Now, the goal of this game for me is to get as many aces in my hand as possible. If I see cards that aren't aces, I'm going to chuck them out, and I'm going to replace it with other cards. I started with this card last time, and I kept it, right? So even though each of these cards was equally likely to be an ace, right, position 1, 2, 3, 4, 5, just like door 1, 2, 3, 4, 5, by showing you which cards I got rid of and which cards I kept means that you know exactly where the ace is. Once again, I'm sending you information even though I have 5 doors that all are the same. But now I want you to imagine another different version of the Monty Hall game, where instead of 3 doors, there are 100 doors, okay? 100 doors. And we're gonna change our description of the game a little bit. So last time we said there's 3 doors, you pick one, Monty's gonna choose one to open for you. I'm gonna rephrase that. I'm gonna say you pick one, and then Monty's gonna open all of the doors except for one, and the one that you picked. So when you picked that initial door, what was the chances that you were correct? It's 1 in 100. Very unlikely that you were correct the first time. Then Monty's gonna open 98 doors. And every single time before he opens that door, he's going to check, hey, does this have the car behind it? No, it's good. I'll open this one for you. By the time you get to the end, there's 1 of 2 possibilities. Either you started out with the correct door, which there was a 1 in 100 chance of happening, or that the car was behind one of those other 99 doors, and Monty has very helpfully described or shown you exactly where it is by opening 98 of them. All right, so the first 8 explanations, they're all pretty intuitive. They're all intuitively based. But maybe you think that I'm hiding something in there somewhere. I'm being a little bit slippery. So I'm going to show you the calculation that shows that you are, in fact, better off switching than staying. What's the expected chance of winning? Where W is equal to 1 if you win, 0 if you lose, if you switch. The expected chance of winning is going to be the probability you started out with the car times what the value of W is if you started out with the car and you switch. And then we're going to add to that, what's the probability that you started out with the goat times what the value of W is if you started out with the goat and you switch. So the probability of starting out with the car was 1/3. And if you started out with the car and you switch, then you lose. The value of W is 0. We're going to add to that the probability of starting out with the goat, which was 2/3, times the value of W if you start out with the goat and you switch, which is 1. The expected value of W if you switch is 2/3, which means that you win 2/3 of the time. So one last thing that I'm going to do is get real concrete. I'm just going to have a computer actually do this for me to show what happens if you make the 2 different approaches. So what I have here is some simulation code in the R statistics language. And so what I'm going to do is I'm going to say, okay, I'm going to randomly select which of the 3 doors, 1, 2, or 3, has the car behind it, which is the car door. I'm also going to say, we're going to randomly pick which door you choose as well. You randomly choose from doors 1, 2, or 3. Then I'm going to determine which is the door that Monty's actually going to reveal. He's going to pick from doors 1, 2, and 3, but he's not going to open the door that has the car behind it, and he's not going to open your door. So let's have that run. Next, we can see, okay, well, what door are you going to end up with if you choose to switch? So based on, if you switch, you're not going to end up with the door you started with, and you're not going to end up with the door that got revealed. Okay, so whatever door is still closed, that's what the door you're going to get if you switch. Let's see what happens there. Now we can calculate, well, what's the result going to be if you stick with the door that you started with? And basically what this is saying is, if the door that you picked at first, your door, is equal to the car door, that means that if you stay, you win. And if you don't, you'll lose. And then finally, what's going to happen if you switch? What this is basically saying is, if the car door is the door that you switched to, you're going to win, and otherwise you're going to lose. Now we can finally see what are the proportion of times that you win if you stay, and what are the proportion of times that you win if you switch. So if you stay, you lose 66.6 or 2/3 of the time, and you win 0.334 or 1/3 of the time. If you switch, you lose 33% of the time, and you win 66% of the time, or 2/3. All right, I hope that makes it a little bit clearer for you. Maybe now you are on board with the idea that if you switch in the Monty Hall problem, you are more likely to win. All right, that's it. Thank you very much.